So in this talk, I would like to show how we used Python scripts in FreeCAD to help with the detector design at HL-LHC. I will start with some brief introduction about the project, and then I will go into the tool itself. I don't think I have to spend a lot of time here to describe the HL-LHC project, just to say that it will really push the technology to its limits with a tenfold increase in radiation doses. So as a consequence, the CMS collaboration is building an entirely new phase 2 tracker with an improved radiation hardening, increased granularity, and reduced material budget. So that project, the CMS tracker upgrade, is bringing together engineers and physicists to design, to optimize, to study, and to plan the new detector. We have several constraints from the existing infrastructure. We have to fit into the same detector using the same service channels. And at the same time, the resources that we have to be shared to the operation of the current detector for run 3. So it's really challenging, and new tools are being developed for that purpose that have no equivalent in previous iterations. And speaking of tools for the optimization of the detector design, and also for planning the integration process. So the CMS tracker is depicted on this slide. Here you see 1/4 of the detector, and it's basically split in two parts. We have the inner tracker that is made of pixel modules, and the outer tracker with two types of modules. What we call the PS modules are detector elements with on one side silicon strip sensors, and on the other side micropixels, and on the outside we have two S modules with two sets of strip sensors. And for this work, it's all about the TED, the tracker Endcap made of double discs, that is that part of the detector. So the fundamental mechanical structure for the TED is what we call a D, and you see a picture here. So it's made of composite material. Each D has a semicircular shape, and it provides the mechanical support and cooling for the detection modules that are put on it. And you see there the 2S and the PS modules. So two Ds form a disk, then two disks form a double disk, and you need 5 double disks to make a TED. And you have two types of these, what we call TED1 and TED2. They are slightly different because of their inner radius. What you see here is the TED1 for the two first double disks, and we have TED2 with a larger inner radius for the last 3 double disks. So that's the device we need to build. Now, in terms of services, each module is a standalone detector, and it is equipped with 3 wires and 2 optical fibers. We have a low voltage differential pair to power the module. Then we have an HV- line to bias the sensor, and we have an optical fiber pair for data readout and communication. The cooling is done through a two-phase CO2 cooling, operating at -35 degrees that is embedded into the superstructure. And all these services are routed first radially on the D to reach the periphery, and then from there longitudinally to the service channels at the end of the tracker volume. And you see there on the photograph how it looks like. The tracker will come in that central area there, inside the greenish calorimeter, and then you have these service channels that are on the periphery. And for the outer tracker, we have 6 service channels. Each of them is split in 3, and we have separate channels for power, optics, and cooling. And this service distribution completely breaks the symmetry of the tracker. And in the end, we have 8 D geometries that we have to consider separately. And you see, for example, for TED1 on the bottom plots, how the optical services are distributed in the different service channels, and how the power services are distributed. So We don't have to go into the details, but you see that it's a totally different routing. So this is an additional complexity. The standard tools in the community in CMS are those three. First, we have to speak about layout optimization, and for that we have what we call TK layout. It's a modeling and performance analysis tools that has been developed at CMS for the study of the silicon tracker, and that can be used outside of it. It is essentially a command line tool that generates the geometry based on simple config files. And then the support structure are added, the services are added. So you have a realistic description of the tracker, and the output from that tool is a Geon4 geometry, web pages, CSV files, and so on. Then we have Geon4 embedded into CMSSW, the CMS analysis software, and it's used for physics performance studies. And it has been used, for example, to produce all the results for the technical design report and for the publications. And finally, when we speak about engineering design, we are usually using CATIA, a CAD software that is essentially an interactive tool with possibilities to script in Visual Basic, and where we will describe all the mechanical aspects and the integration with other subdetectors and so on. What we are missing in this very specific project is something that combines interactivity, interoperability with the different other tools, with Geon4, with the TK layout, with the HEP ecosystem in general, and also something that has automation built in because of the many different geometries that we have to design and study. So we want to create several variations of the base model. We need to navigate and visualize the geometry and the logical organization. We're interested into the geometrical hierarchy, the unique ID of each module and so on, but also of the grouping by power, by optics, by cooling, by service channels, etc. We also want to study the service arrangement, combining mechanical and physical aspects, and potentially many more. So in that context, we tried and we wanted to investigate the use of FreeCAD. So FreeCAD is a general purpose parametric 3D CAD modeler developed completely open source with an GPL license. FreeCAD is aimed directly at mechanical engineering and product design, but it has also a wider range of uses. You can use it for architecture, for finite element analysis, for 3D printing, for CNC, and so on. Its main characteristics are that it is feature-based parametric modeler with a modular software architecture, and it's possible to provide additional functionalities without modifying the core system. What is interesting for us today is the following statement that appears on the website of the project that says that FreeCAD is built from scratch to be totally controlled by Python scripts. Almost all parts of FreeCAD, such as the interface, the scene content, and even the representation of this content in the 3D views, are accessible from the built-in Python interpreter or from your own scripts. As a result, FreeCAD is probably one of the most deeply customizable engineering applications available today, they say. So, for us, what were the design choices? First, we aim at an open tool for experts. So we decided to develop within FreeCAD to use its interface. The alternative would have been to use FreeCAD as a library with a custom user interface, more restricted. But here we really wanted something open. Then, since we were not sure about the capabilities, we wanted to go for incremental development with well-factorized units. So we went for using macros. Macros in FreeCAD are basically Python scripts that are executed within FreeCAD. There are alternatives, for example, to use what they call FreeCAD workspace, but then you have an additional overhead, especially at the beginning of the project. And also, we wanted to have access to the cabling information from within FreeCAD. So we decided to include all the relevant information in the model itself. So that's once created, the model is a standalone representation of all the information that is available. A disclaimer here is that I'm neither a FreeCAD expert. I discovered the tool like 1 year ago, and I'm not a full-time Python developer either. So you can take it as an adventure that took a few months. But this is part of the equation, and you will see that we can do already a lot in that context. So first, few words about the organization of the FreeCAD models. We have a relatively flat structure. So here you see a logical representation of one file. We first have the D mechanics. Then we have a set of hidden module templates that are used when we populate the geometry. And then we have one group per module. And within that group, you will find the geometrical representation of the module, cabling information, and that cabling information is an app feature Python object, basically a list of properties with their values. And this is how you see that in FreeCAD. You have a little table with the different entries and their values. And then you also have all the services that are attached to the module. You have both the 2D and the 3D representations that are visible there. So I will now go through a few use cases. I will show some Python code, mostly to show the API that is provided by FreeCAD, and then I have some screencasts. I decided to pre-record some examples so that I can speed up the replay to save a bit of time. But for the question time, if you want, I can do some live demo. So the first thing to create a model is to generate the support structure and then iteratively put all the modules, the PS and the 2S modules, using the coordinates and orientation from the TK layout. And the third step is then to add the logical cabling information using the app feature Python object. And you see here the code that is used to place one module on the mechanics. So you have a method to access the current document. Then you can add an object. We add a group. And in that group, we add a module. It can be a 2S or a PS, depending on the case. And we set the position and the placement. So the placement is basically the position and the orientation. And that's it. And you see the API is pretty straightforward. So then when you run this kind of scripts, this is how it goes in FreeCAD. We select we first create the mechanics, and we select the data file with all the coordinates, and here we populate on one side of the D. You see it's putting first the PS modules and then the 2S modules. What you can see is that we've created additional buttons in the interface, and each of these buttons are linked to a single script, a single FreeCAD macro. Okay, now we'll go to the other side of the D, surface 1, and again, we repeat the process. So yeah, the model is basically ready at this stage, and you can see on the side that the file is now populated with the mechanics and all the modules. And the last step that we'll do here is to set a color. We'll use color to encode some of the cabling information. So this is what we just saw. We can also use a color scheme to relate to some of the cabling information. And for that, we want to loop over all the modules, so we access them in the active documents based on the type and name. And then we access the cabling information, get some property, and use that to set the color. And setting the color is nothing more complicated than accessing the module, again, by type and name, and set the shape color of the corresponding view object. And that's it. So the result for us is that for given geometry, we can get different versions, different colors, and have a description of the optical group, of the optical service channels, of the power service channels, or of the test group for the integration tests. So it's really easy to inspect the logical cabling based on that. Third use case is about services. The model we have for the optical fibers and wires has been developed in LaTeX using the TKZ package for historical reasons. And what we have is for each of the D geometry in each of the side, we have a SVG object that contains all the different paths. So what we need to do is to import the path in FreeCAD, extrude them as 3D object for a more realistic visualization, and then we can do some in-depth analysis. So we can look at the length, at the curvature, check the routing, make sure that the model follows the various kinds of constraints that we have. And you see here, for example, two results that we obtained with Matplotlib in a later step. The first one shows the curvature along a given optical fiber. So what you see is the XY position on the DE, and color coded, you have the curvature. Another result is about the length. So this is the length of the individual optical fibers, and just integrating, you can get the total length. That is something like 1 kilometer for one Endcap. And of course, we can do much more from the model as soon as we have it. So how do we do the import? Again, I will not show the full code here, but you can see that well, there is a first step that is about getting all the fiber object and grouping them by name. And then we loop over these groups. For each group, we create a sketch, so a 2D object, just with the FreeCAD method. And then we have to specify a few options. We can add constraints. So the sketch that is obtained there is made of individual paths. Well, the constraint that we add there is that these paths are connected. So it will ease the manual modification later on if we want to. And then there is we call another small method that is just putting that sketch in the group of a given module. So this is that's script and a bit more executed. So we load an SVG file. We have to specify on which side of the D we want to import the cabling. There is an automatic pop-up about the scale, and now FreeCAD is loading the SVG object. There it is. And now our script is looping over all these paths and is creating sketches that will then be put on the proper location on the D. This is a relatively fast process given the complexity of the task. And in a second, you will see all the services that have been imported on the model. And here you see a zoom on part of the surface where you have the various services, power and optics installed, and in that case also extruded in 3D on the surface. One last use case that I want to mention is about simulation of the assembly sequence. So once we have a full model, we want also to simulate how will be the work in the lab when we integrate the various models on the mechanics. So we have a sequence file that tells us which modules comes first, and we want to simulate that in FreeCAD. And I show that because scripts can also be used to add some user interface elements to FreeCAD. And in this case, we add a side panel, and all the callbacks for the different UI elements are functions defined in the macro. And the code for that is pretty standard if you know about Qt and about PySide. So it's we use in this case the UI loader. We load the file. That file has a description of the user interface. There is some configuration to be done. That's why we define the callbacks. And then to add it to the FreeCAD window, we just call this method to get a handle on the main window, and we added a widget. So it's pretty standard PySide code, plus some very light FreeCAD additions. And yeah, here is a small demo. We execute the macro. This creates the side panel, and then we use it. We load the YAML description of the assembly sequence, and then we can go through. We'll see in this case we even select. We have another focus mode that will zoom on the component that is being processed. And you'll see here we put a module, we connect the power, we connect the optics, we move to the next module, we connect the power, we connect the optics, and we go on with the third module and with more. And at each step, you can see on the side panels that the object that has been processed is highlighted. You have all the information about its position, and you can easily access the corresponding cabling object from the code. Here we go on without the autofocus mode. We can also go quickly to later steps, or here we go even to the other side. We'll go a bit further, and then there is also a mode where you can just automatically play the sequence from a given place. And here it goes all by itself. So it could be used to make a recording and have a small movie. Here, of course, it's a random sequence. We still have to decide on the exact assembly sequence, but this gives the idea. Okay, so it's already time for the conclusions. Just to say that the construction of the new CMS central tracker for HL-LHC brings new challenges because of the size of the project and the complexity of the detector. And using Python allowed us to make FreeCAD into a wonderful tool to manage the construction project. So we use everything that the use of Python in FreeCAD makes it very versatile and easy to interface with other tools. You can control most of the elements of the user interface. So we used it mainly to extend the application for our needs, but you can also do the reverse, and we have some projects for that. You can use FreeCAD as a library, as a Python library in your own project. I've not shown that, but there is an integrated Python console, and it's pretty useful because it displays the commands for each action in the user interface. And it's a great way to learn the API just by doing. You select a component, you change the color, and then you see what are the Python calls for that action. So all the tools that I've shown today were developed in less than a year without prior knowledge of FreeCAD. I think it corresponds roughly to 3 months work, looking at the GitLab logs, and the full set of scripts are something like 2,000 lines of code. I think all this makes it a good candidate for any project that needs a 3D dynamic visualization of a CAD geometry interface with other components in the HEP ecosystem, be it Matplotlib, Root, Geant4, you name it. So I will stop here, and of course welcome your questions.
Thanks very much. That was very interesting, a bit different from what many of us do as an analysis work, so to speak, but it was still interesting to see how you can solve it with Python. So you have a few questions there.
Yeah, okay, let's go through. So if FreeCAD is passing 3D visualization through customizable Python, is it using NumPy array for performance or for loops? I've not seen any use of NumPy in the FreeCAD code, in native code. but you can use it yourself. Yeah, there is no restriction on the kind of library that you will use in your project. Right now, FreeCAD is using Python 3, PySide 2, and you can load, you can import any package that would help for your project. Now, whether they could gain in their internals, I don't know. They're already using pretty advanced open source libraries for most of their work. They are using Open Cascade, for example, for the 3D part. So I hope it answers the question. So if you found limitation compared to other softwares for your own work, as I said, for the Python part, it's pretty open. I've not seen in any place a limitation in the kind of package you can import. So even if it's a macro, you can really consider that as a Python script. And if you want to do things, well, maybe one thing, it's if you develop your own Python library, it may be tricky to import it in a macro. If you want to do that, to build bigger projects, then it's probably better to start creating a workspace, and the Python code behind the workspace will then be a full Python module. And then you can develop just your module and do whatever you like. And then for the link with DD4HEP, I think it could be done. Yeah, I was thinking about that while preparing this talk. Here we just went straight from the description we had, because there is this sticky layout code that generates a CSV file with the coordinates and angle of all the components. And we already have CAD representation of the modules, the 2S and the PS modules. So we were just loading the step files, and from this 3D description, well, we basically copy paste the modules in the proper place. But we could certainly have a more generic development that takes DD4HEP or any other Gen4 geometry description and translate that into a FreeCAD model. Yeah, FreeCAD is basically built from basic volume. Well, the description of objects in FreeCAD is made of basic volumes. So you just have to describe using FreeCAD classes, or you build your scene. So if you have it already in some format, it's just a matter of writing the translation, some reader for in that case, DD4HEP, that creates the corresponding content in the scene. Yeah, I see no technical problem with that. It's a bit of work, probably.